Or turn off your video. Yep. All right. So as I say, I have started recording. I would now ask Swapna to introduce our speaker for this evening. Please.
Yeah. Thanks. Thank you, Alan. Welcome everybody. It's a very exciting talk today. I want to welcome Dr. JJ Kavelaars. He is a Ontario-born BC resident, so very happy to have him at the RASC Mississauga. Dr. Kavelaars is a principal research officer at the National Research Council of Canada's Herzberg Astronomy and Astrophysics Research Centre, where he has worked since 2002 and has been the head of the Canadian Astronomy Data Centre since 2019. Dr. Kavelaars researches the sky for outer solar system objects and has discovered dozens of satellites of the giant planets and over 1,000 minor planets in the distant solar system. He's a co-lead of the Canada-France Ecliptic Plan Survey and the Outer Solar System Origin Survey, and co-investigates on the NASA Horizons Kuiper extended mission. Dr. Kavelaars has served on numerous national and international science committees, organized science conferences, and contributed chapters to review books. He has co-authored over 100 peer-reviewed science articles, and his research has been cited by his peers over 4,000 times. So welcome so much. Welcome, Dr. Kavelaars, to our talk tonight, and look forward to hearing from you.
Thanks very much, Swapna, for that introduction. That's funny to hear that read out. There was a discussion of New Zealand there going on. I was just going to let you know that I have a former postdoctoral fellow of mine, Michelle Bannister, is now a faculty member at Canterbury in New Zealand, and does excellent public speaking. If you're ever looking for someone to go to a public talk on, Michelle is absolutely fantastic. So I'll start off here. I've got this slide presentation of what we did with the encounter for discovering Arrokoth and flying past it, and what we learned from that. And I'm just going to start the slides. And now I've lost the other things. I have to share the window. We did this before, so I'm almost a pro at this point. Yeah. There we go. That's the one I want to do. So I think you should all be seeing my presentation slide now, which is great.
Yep.
Good stuff. Okay. So yeah, so my name's JJ Kavelaars. Did my graduate work at Queen's University in Kingston, Ontario, and then was at McMaster for a short period of time, and then came out to here in British Columbia, where I've enjoyed being for quite some time now, for 20 years. This is a picture of an artist's conception of what we were going to do. So I started off by showing you, before we'd actually been to Arrokoth, one of my grad students, who's artistically, and well, he was at the time a grad student, now he's running his own research institute, in fact, really artistically amazing. And he made this graphic for us of what he thought we would be seeing when we got to Arrokoth. So this is a pre-encounter image, predictive of what we're going to see based on the knowledge we had prior to the encounter. So you can see here a large lobe and a small lobe, or a large body and a small body orbiting around each other, or maybe in contact. It's hard to tell from this perspective. Heavily cratered body. There's all kinds of craters on the surface of this thing. And then you have the spacecraft here flying right past it. Perfect flyby encounter, worked perfectly. That was the prediction. It's quite brightly illuminated. I pointed out to him that the sun is in the background, right? The spacecraft's coming from the sun direction. There's no way there's going to be this much light when we get to Arrokoth. It's so far, right? We're talking about an object that's 43 point something astronomical units from the sun. So that's pretty faint by the time you get out there. The sunlight is dimmed 1,600 times compared to what you see on the Earth. So it's like a very, very dark evening as opposed to a sunlit thing like this. But Okay, so the journey started though for us even before this. This is from the launch back in January of 2006.
Horizon spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
So I just point out that they told us it was a decade-long mission, okay? And that was in 2006. We encounters in 2019, so just slightly over that decade mark that they predicted. And the mission is continuing to go today. What you're watching there with this liftoff is the most, the fastest liftoff of a civilian spacecraft in the history of NASA. So there was this idea that Pluto was its orbit was getting farther and farther from the sun. And there was this worry that the atmosphere of Pluto would slowly condense out as it cooled. And so we wanted to get to Pluto as fast as possible. And so the trajectory of this spacecraft is basically a bullet going from the Earth to Pluto. And this makes it's going very fast at the time of launch. It was in the 23 kilometers per second range. By the time we got out to Pluto, it was down to 16. And by the time we got down to Arrokoth, it had dropped to 14. So, but it's still a tremendously fast launch.
That's 15 seconds. Everything continues to look good as the Atlas V vehicle climbs away from Florida's east coast. 5 solid rocket strap-on boosters are burning just fine, sending the New Horizons spacecraft on its way to the very edge of our solar system.
So you can imagine for the science team, this is a very dramatic moment in our lives because we're basically watching as the thing that we've spent all this time trying to work on is lifted off the Earth by rockets that we think will work fine. They've been tested. So this is the spacecraft itself. This is New Horizons. It's about the size of a Volkswagen Beetle, we like to say. That's about the size of the spacecraft. It has a series of instruments on board. The most important one for this mission was the LORRI imager, the long range reconnaissance imager. LORRI takes basically the black and white photos in visible light. Ralph is a color imager, slightly less sensitivity, slightly less resolution, but provides a color component to the observations. And then for New Horizons, for Arrokoth, encounter with Arrokoth, you know, we're going to be past where we're going to worry about ultraviolet emission. There's not going to be a radio signature off of this object. There won't be any real solar wind activity going on. So those instruments, they're much less important. But the very bottom of the list, I want to draw your attention to something called SDC, which is the Student Dust Counter. And this was an experiment that was added onto the spacecraft after it had already been designed, essentially, and is a student-led initiative at the University of Colorado to build a dust impact experiment so that as the spacecraft is flying along, the side that's pointing into the forward direction, kind of like it's pointing downstream, dust particles hit this detector, and we can count how much dust there is in the outer solar system. And that is the only dust experiment that has ever properly worked in the very distant solar system. And it was built by some graduate students and some undergraduates and strapped onto the spacecraft as kind of almost an afterthought. And is providing us with very interesting information about the dust population, so much so that in the extended mission phase 2, what we've decided to do, or we asked NASA for permission to do, is to turn the spacecraft so that the antenna that you see there, this big giant Rex antenna, instead of us using that to communicate with the Earth, we want to point it in the direction we're going and have dust hit it. And we can count the dust hits by their radio signal, and it will be the biggest dust collector experiment that's ever been done if we get permission to do it. So, which I'm pretty sure we will. So, okay. So, so this is the system Pluto that was first got the first thing that New Horizons flew past, and these are the images from New Horizons. Pluto, Charon, and then its very small moons, Styx, Nix, Hydra, and Kerberos. You know, the heart on Pluto was a fantastic thing to see, the beautiful glacier on the surface of Pluto, this nitrogen glacier that seems to be refreshing itself, the incredible compacted terrain here along the edge of Charon, the impact cratering, the very interesting methane on the pole of Charon, these large deposits of methane that seem to be circulating around the planet, sorry, up here around Pluto, and then this dark red material, which is of particular unknown chemistry, so which we're interested in understanding more about. But that's Pluto. But it was such a fantastic encounter. I just want to show this lovely montage, basically, all the photos that were taken as we flew close to Pluto. Pluto is many times that, many times bigger than Arrokoth. Arrokoth is the size of these mountains that we're seeing as we fly along here. So the rich diversity of terrain, the beautiful glacier of nitrogen ice there with its convective cells showing up. The mountains themselves are floating ice mountains. They're like giant ice cubes floating on top of the nitrogen. And the whole landscape is just full of rich diversity that is still being studied by mission team members and by people outside of the mission team. You can see this glacial flow is just fantastic. It's really, I mean, when you've seen geology and you see this is such amazing geology on Pluto's surface. Okay, so when we left the Earth, this is what we knew about the Kuiper belt thereabouts. So this is an image from 1999. So it's a little bit before we actually launched, but it's actually consistent with around the time that mission planning locked in. So with a space mission, you really are locking in what you're going to do years in advance of actually doing it and deciding this is what we're going to do, just in general. So the rocket has to go to a particular place. You have to decide where it's going to go, and that's done years in advance. So around the year 2000 was when we locked in most of the trajectory of New Horizons. And the idea was that we were going to fly out and visit Pluto, which is way down here in the bottom corner. And then we're going to be going so fast, we can't do any real course correction. We're just flying out of the solar system, and we're going to fly into this completely empty part of the solar system, and we're going to observe a Kuiper belt object. Each of the dots on this plot represents a known object in the outer solar system. So it's a Kuiper belt object we already knew about. The blue ones are things that are in low inclination orbits that are going around the sun in a rather normal sort of way. The black dots, the filled and open ones, are things that have a dynamical resonant interaction with Pluto, with Neptune, sorry, just the way Pluto does. And they have a peculiar kind of orbit. You can see there's a few oddballs here. There's a green dot, one over here. These are objects that have very peculiar orbits. There were 2 of them known, or 3 known at the time of this one. And then this red thing, which has a slightly higher inclination orbit. So really sparse information to plan a mission around. And essentially, it was a shot in the dark. It was the Hail Mary pass at the football game, where we said, once we get past Pluto, we're going to we'll search for something else to go to. Okay, we don't know where it is right now, but we're going to do a search and we're going to find something at the time. So in 2012, we started the search in earnest. And the problem with the sky is, in the direction that the spacecraft is going, it's flying towards the galactic plane, essentially. And so when you take a picture of the galactic plane, you see a lot of stars. So this is just a zoom in of a generic image in the direction that we were searching for something that we could fly the spacecraft to. In 2012, we still hadn't found anything. This is a ground-based image, and it was just too crowded with stars. We used as many tools as we could, and we did pretty well. We do this star subtraction technique where we can take images in a series, and then we can use those images to build a template that looks like the stars. And then we subtract that template image from all the other images individually, and then we re-add all the images, and we look to see what we get. And when we do that for this particular field, we see this. So we've removed all the stars by the subtraction technique. It's still pretty noisy, but you can see here that I put this red circle around to draw your eye. This is an actual Kuiper belt object. It's not Arrokoth, but it's an actual Kuiper belt object in the outer solar system that was found in this image. But this bright thing over here, this is a variable star. It's just gotten brighter in that image data. And here's another variable star. And then all of this stuff is just noise. This is just a bit of noise from the subtraction. It's very messy data to work with. We've gotten very good at it, and we know how to work with it, but it's messy data. So we did that search in 2012, and it wasn't working out. the encounter with Pluto was coming up. We knew we had to focus on the encounter with Pluto, but we also needed to know what we're going to do next. And so we had to make a plan. So that's actually where the Canadian component of this mission really kicked in. So I'm a co-lead of a mission that was called the Canada-France Ecliptic Plane Survey. And what we have been doing since the early 2000s, after that plot I showed you was made, what we've been doing is we've been observing the outer solar system and trying to understand the structure of the Kuiper belt in minute detail to really understand what was out there. And we had detected 183 Kuiper belt objects over the course of a 7-year observing campaign, okay? So these are not coming in fast and furious. This is really painstaking work to get these 183 objects, but it's a very good sample for doing statistical analysis with. And from that, we were able to come up with a model of what we think the Kuiper belt looks like. And I'm showing you a slide on the right-hand side there that is an XY plot. So this is looking down from above the solar system. The sun's in the center of this diagram. Then we have Jupiter and Saturn and Uranus and Neptune are those red lines. Those are the orbits of those planets. So we're looking down, we see those planets' orbits because that's how they magically project onto the sky. And all the little black dots are objects in our model of what we think the Kuiper belt looks like. So this is not objects we know about. We only found 183, but we discovered that we had to make this model with a lot of intricate detail to explain the full range of what we saw in that sample. We took that model and we started saying, okay, this model exists in 2011. What do we expect we could actually do? So we started doing really detailed analysis of trying to understand how hard is this problem of finding a target for the New Horizons spacecraft. So there's a bunch of points here that are interesting for some people, not for others, but I will kind of draw your attention to the figures. So we're dealing in looking in R-band magnitudes. So you probably are familiar with using magnitudes to describe how bright something is. Your eyeballs are maybe 6th magnitude. If you have something like a 30-centimeter telescope, you can probably pick out 16th magnitude stars if you take a good exposure on the right night. That's going to be close to your limit. And if you stack a whole bunch of them, you can get a little deeper. What we do here is we're trying to find something. This little blue dot is a model of the Kuiper belt of how many things we think there are if we can get to 26th magnitude in R-band, which is deeper than anyone really had ever surveyed the outer solar system. And all of these lines that are shown on here are different models of what we might expect to see based on that CFEP's, the Canada-France Ecliptic Plane Survey work. So what we predicted was that if the spacecraft could make a 1 kilometer per second course adjustment, after Pluto, we would see, and we could get to 26 magnitude, we would find 20 things that the spacecraft could go to. All we needed was a kilometer per second of fuel. Unfortunately, we only had about 130 meters per second of fuel adjustment available. And now we're down to 2 or 3 things that will probably show up if we can search to 26 magnitude. This can't be done from the ground. In that dense stellar field that I showed you, there was just no way to do this from the ground. And so we had to do it some other way. And so we needed to propose to the Hubble Space Telescope to do this project. This is another kind of plot that we showed to the folks at Hubble to try to convince them we actually knew what we were talking about. We said, here, look, we discovered a whole bunch of things in our search so far. And if we had 200 meters per second of fuel, we've already found 2 things we could go to. And if we had 300, we found somewhere between 1 and 3, depending on exactly how good our observations are. So we have this distribution of things. And the problem is that our available delta V is down here at 150-ish. And we just haven't found anything in that zone. But everything else about the model's working. We're just not getting deep enough. If you give us time on Hubble, we'll do it. They were very skeptical and they gave us a test program. And they said, okay, well, here's a little test program. You guys can have 5 orbits of the spacecraft Hubble, and you can use those to test out your idea. And then once you've demonstrated that it works, if it does, we'll give you more time. So we did that test observations and they worked. And so Hubble said, okay, here you go, here's what you needed, and you get the whole thing. We got 166 orbits of the Hubble telescope. That's something on the order of a $4 or $5 million US investment in this program. It's just an enormous amount of time. It was the largest allocation at the time to any solar system observing campaign. It took a lot of pressure from the team to get Hubble to agree to it, to get the time allocation committees to agree to it. It just was crazy. And what was really kind of really pressed the whole thing home was that we basically had about a year to go from acquiring this data, analyzing this data, discovering the object, following the object, figuring out what orbit it was on, and then program that into the spacecraft. We knew we had about a year. But we thought if we did this, we could probably get to 27.5 magnitude with Hubble. Turns out we couldn't. We didn't actually get that deep, but we got as deep as we needed to get. So we did the search with Hubble, and this is what it looks like when we take that same technique that I showed you the first time, only now it's with Hubble data. And because Hubble's so stable and the cameras are so good, you can subtract the stars and they just go away. And so we had a set of images here on this one side. We have a set of images that bling, out came an object. And we have a set of images taken a bit later, and bling, out comes that same object. And I'm just showing it here. It actually appears in the individual exposures. You could never pick out that that was a Kuiper belt object. You know, you can see all these cosmic rays that are dancing around on the image. So you could never do this just straight up. You have to do this differencing technique and remove the cosmic rays. But once you've done that, you can go back and put a green circle on the thing that you know is the right object. And so that's what we've done here. And that object is about 26.3 magnitudes in brightness. And we found 3 things that were encounterable within that 150 meter per second range. And, you know, we're scientists. We made a prediction. We thought there would be somewhere between 1 and 2. Up here's 2, here's 1. So we underpredicted by a lot what we thought we could do. But we actually managed to get 3 things that were in that zone. So, okay. So, in 2019, we were really excited because we were about to make our first ever observation of a new world in the outer solar system. And I'm showing you here a simulated view of what the science team had basically decided this is what we're going to see. Okay, so I showed you the one from the grad student at the very start. That's what the grad student had kind of thought was going to be happening. Pre-encounter, this is what we were showing to science committees, that this is probably what we're going to be looking at when we get there. Okay, one more look at Pluto, because it's 2014 and we've really enjoyed visiting Pluto. And we look back and we see this beautiful haze atmosphere looking back at Pluto's sky. And so this is just the blue light of the sun refracting through Pluto's atmosphere. And you can see these lovely layers in the atmosphere, these different pressure layers. Atmospheric scientists studying planetary atmospheres get a lot of joy analyzing this data. And you can even see how some of the light is bending around here, and you're getting this scattering into the very upper parts of the atmosphere in this cold, unlit area of Pluto. Okay, and so onward to new horizons. We knew that the flyby of Arrokoth would happen on New Year's Day, 2019. Now, I'll admit that the encounter could have happened on the 27th of December, or it could have happened on the 3rd of January. We did have a little bit of fuel available to time the encounter. And after some discussion, it was decided to use that small amount of fuel to make the encounter happen on New Year's Day, just as a nice place marker for the start of 2019. And we decided we would fly past at 3,500 kilometers in altitude above the object. And at that height, we thought we'll get the highest resolution images of an outer solar system object ever attained. The fly past Pluto was at 5,000 kilometers. The reason to stay back at 3,500 kilometers from an object that you think is going to be 100 kilometers in size is so that the camera field of view can actually capture the entire object. If we got in really, a lot closer, we would just have a part of the surface. 3,500 kilometers was our prediction of how far out you had to be to see the whole object at closest approach. And then there's a new artist concept image was put together. This is a new one. You can kind of see the evolving ideas of what we're going to see. We have this model of the Kuiper belt that was put together by the CFEPS collaboration. And we put it right on the cover of the proposal because it was the thing that allowed us to actually find this target to fly to it. So, okay, so there's the model of the Kuiper belt. Oh yes, and back at the time when this slide was made, this was made prior to our actual encounter, or just this one's actually from just right after the encounter. We were naming the object Ultima Thule. So in some of the slides, I have Ultima Thule as the name of the object. This was kind of like a placeholder name that we used. Now the name of the object is Arrokoth. And if you want, at the end, I can discuss how naming works for objects in the outer solar system. So this is a nice little model that I showed at the start as that kind of top-down view. Now we kind of see it in this angled perspective. You have the Kuiper belt model from the CFEPS collaboration. Then we have every known Trojan, or every known asteroid, sorry, in here. So these are all the asteroids in the asteroid belt. And then we have a few large Kuiper belt objects that have names that people might remember or might know. I want to just point out how many more objects there are in the Kuiper belt than the asteroid belt. The asteroid belt is a puny little remnant of formation of the inner planets. The Kuiper belt is just this much more massive remnant, except it's only a few hundredths the mass of Earth, okay? So all those objects you see out there in the Kuiper belt, they don't make up any real mass. They're just a few, 5% the mass of the Earth. It's very, very light. So, but finally, we're going to explore this third zone of the solar system. Okay, and this is a little video that one of my other graduate students put together that I found was really informative of what we're going to see. So you see there's the little triangle that's flying along. That's the spacecraft. We put a circle around Pluto. We put a circle around Arrokoth. Every known object in the Kuiper belt is on this slide. Do you notice that where we're flying, there are no known objects in the Kuiper belt? It's the galactic plane. It's just not possible to find things in the galactic plane. That's how hard that was. And you can see this little line along here of things that are known. And that is the Hubble search, looking in that one direction and bling, 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 finding all kinds of objects. So there's a little kind of object lesson. There's a lot of discussion of something called Planet 9 or Planet X, an extra solar system, an extra planet. And what the scientists who are advocating that there's needs to be an extra planet is that they notice that there are no objects in this direction that are close to the sun, that have really large orbits. So they're close to the sun today, but they have very large orbits. There are many objects over on this side that have been found that have these large orbits that come in a bit closer to the sun. And so they say, well, that means that there has to be this massive planet out there that's aligning the orbits in this way. And these have really large orbits since they're being aligned by this tug from the sky. But the scientists who work in the field who look at this planet, well, the reason we don't know about things in this direction, it's nothing to do with a massive planet. It has to do with how hard it is to look. So it's very hard to look this way, and it's very hard to look over on the other side opposite. And that's the galactic plane going through. Looking in this direction is much easier. And then looking in this direction is actually like, so the galactic plane's sort of about here, and then you go down here and it's also a bit thin, and that's February. And it's just hard to do observing in February in the north because of weather. So anyway, let's go back to Arrokoth. We've got the spacecraft flying along there. It's following that white trajectory line. And let's see if I can get it to fly past Pluto here. So there it goes. So there's the encounter with Pluto, and there it goes past Arrokoth. And this whole thing's going to tip over a bit, and we're going to blur out a whole bunch of the objects. These things in red are these objects that are in low inclination orbits close to a very thin disk. It's one of the thinnest structures in the solar system, given the scale. So this disk of material is 45 astronomical units out, and only about half an astronomical unit thick. So it has a ratio of about 1 in 100. So it's a very thin structure of all of these objects orbiting around in this disk. Okay, so what's the Arrokoth encounter going to be looking like? It's way more challenging than the Pluto flyby. The target's 80 times smaller than the diameter of Pluto. We're going to fly 4 times closer. So we're going to need way more navigational precision, even though the target was discovered in 2014 and we're going to fly past it in 2019. Pluto, we had decades of data to get a good orbit for. this thing, we were really flying by the seat of our pants. The uncertain target location is just crazy. The period of the orbit is 293 years, and we discovered in 2014. You don't get much of a knowledge of that. We don't know what it's like out there. We have no idea how much dust there is. We don't know what kind of object this is going to be. The surface is super dark. Even compared to Pluto, it's already 4 times less light than at Pluto. The light from the sun is dropping off rapidly. We have almost, well, not almost no, but we're very limited spacecraft power. So much so that we're worried about running more than 2 instruments at the same time. So we're going to be switching off and on things as we go past, which is going to kind of annoy some of the science team members whose instrument will be turned off during the encounter. But we were pretty sure there wasn't going to be any radio signal coming off this thing. And then we have about a 12.5 hour, 12.25 hour round trip flight time. So it means basically a day before the actual observations is the last chance we have to adjust anything. And is what we did the very day before we made the last corrections to the flyby course. This is kind of a graphic to kind of give you a orientation to the system. Again, this object was known as an Ultima Thule right after its discovery. So this is the trajectory of the spacecraft coming along here, this white line. Here, sorry, the sun. This is the orbit. This is the orbit of the object going around the sun. Here's the object itself. The sun's illuminating this side is in shadow. And the spacecraft's flying along here, and this distance here is about 3,500 kilometers. So it's just, here's the object, and we're gonna go whoosh by it over the top. We had a 3-day conference to discuss whether we should fly over the top of the object or underneath the object, okay? This thing was, we planned everything as best we could and had arguments about every detail of this mission. I think we made a lot of very good choices. Okay, then while we're actually on our way to Arrokoth, we have to track the spacecraft. So that's the NASA's Deep Space Network, which is a bunch of really large antennas. The one in Australia turns out to be incredibly important for this mission just because of we needed to be able to look in that direction during this time. So it's fantastic that we have that facility there. We also, though, at the time of encounter, basically any large antenna NASA had access to was listening for Arrokoth signals. We could start making adjustments, and the last pointing correction happened on December 30th, and the actual encounter happened on the 31st. So we were tweaking exactly where we were going to point right up to the last minute that we could do. This is what data looks like from the spacecraft. So on the far left, you see what our raw images look like, okay? This is not the pretty, I mean, I'm going to show you some really nice pictures, and I just want you to appreciate that, you know, there's a lot of processing that goes into turning these into nice images. So what you see on the other side there, you see this thing that, oh, we just flew close to it. That's Arrokoth moving there through the field, okay? That was this little white blob moving south through this field. It's going to play on a loop. Everything else in there is stars. Remember, this is a galactic plane, so there's all these stars everywhere. This was us on December 3rd, 4th, 5th, trying to figure out where the heck is Arrokoth? Where is it? We know it should be there, but it wasn't until about the 5th or 6th of December that we could finally say, yes, we can detect from the spacecraft the object. So with less than a month before the encounter, we managed to detect, that's where the object is. Right there, you can't see it. In October, it's really hidden. And then it pops out of the data here on around December the 5th. There we go. So easy to see now. And there, you look on the other side where you can see the star subtracted version, which is much easier to see it in. And then we get very close. Now you can kind of see that it's changing brightness as it's coming in. And we started to realize that, oh, we're seeing different orientations or perspectives on this object as we go along. So, okay, so this is a little map. The reason I'm harping on this navigational thing is that this was a critical part, and Canada's role here was amazing. So what we did was we had this, we did these observations, but there was no good sky chart available at the time. So where the stars are was not known very precisely in that field. Gaia had not yet operated. So Gaia is a fantastic instrument that has mapped the positions of all the stars to super high precision. It wasn't available at the time that this was happening. So what we did was we used the Canada-France Wide Telescope to observe the part of the sky where the spacecraft was flying, and we built a brand new high precision reference frame for this encounter to happen. Without it, this encounter would not have occurred. And it's just that we happened to be very fortunate to have a fantastic instrument on the Canada-France Wide Telescope called Megaprime. It's able to take really very uniform pictures of the sky that you can make lovely plate solutions for. And then we can tie those plate solutions into the stars in the images that are being seen by the spacecraft and the stars that are being seen in tracking observations from Hubble. But all though tied back to linking it to that CFHT data. So eventually the encounter is going to happen. You see all these little arrows. So we're flying along here, and at TCM 22, this no-OC thing 5 is a code for the observation correction. We're flying in this direction. Now we're flying here. And then we did some more observing from the ground and tuned up where we thought the object was, and we started flying in this direction over here. And then we started flying over here. And now we have to zoom in a little bit so we can actually see what the heck's going on. So we zoom in a little bit to see here. Here's where we were flying. Then we shifted down to here. But you can see that all of this happened, clink, 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 to try to finally get to the point where here is where the target actually was. So as we're flying along, we are just adjusting our course and flying along through this with each observation. Some of these were, for instance, here we have this EY1. This was one person's analysis. She said, I think we made some mistakes in our previous analysis for this correction over here, and that we need to make this adjustment. So we need to fly over to here. Okay, we made that. Then someone else made another calculation. No, we need to be flying here. And then finally we made a correction to go over to here. So, and that turns out, then we went up to here and then we came back down here. So it's kind of jiggered around a little bit, but all of it was a result of that tie-in with that astrometric reference from Canada. Okay, so what are the science objectives here? We're going to map the geology and morphology of Arrokoth. We're going to map the surface color and the composition. We're going to try and find out if there's any ice on the surface, ammonia ice, carbon monoxide, methane ice, water ice maybe. And then we want to know what makes Arrokoth dark and red. It's basically red like that part of Pluto that we don't understand. So these are kind of the high level goals that we wrote down as things we wanted to do. Okay, the actual encounter here, I give it to you here. Each of these tick marks is 15 minutes of time. So here the spacecraft is here, and then an hour later it's here, and then an hour later it's here, and it's gone. The actual observations sort of start back here, right? So we have about a 2-hour window of observing, and we see here we get our best infrared observation is going to happen here. Our second best infrared observation, sorry. Then we're going to get a thermal measurement. Then we're going to get a color measurement. Then we're going to take our best infrared. And you can see that these little bands, each band is a different instrument operating, and we only have 2 instruments operating at a time. We'll finally get down here to the best black and white image being taken right here, and a crescent image that I'll show you taken here. And here we had both the LORRI and the MVIC, the color imager, at the same time observing. And then you see this little purple rectangle. This is where we don't know where Arrokoth is. Arrokoth is 50 kilometers in size. It's just a little tick mark in the middle of this box, okay? But we don't know exactly where it is. So when this was made, this planning diagram, we have this very large area it could go. Okay, so what do we see? These are images that were taken on December 30th. This is 1 day prior to encounter. The last tweak of the spacecraft happened. This is the raw image that came from the spacecraft, and this is after doing some sharpening, some nice processing. So we actually do stuff that you might watch a TV show and they're like, oh, the face is all blurry, and then suddenly, oh, sharpen that up. Now you can see the person. We kind of do the same thing with the spacecraft. We have a large series of images. We understand the point spread function of the camera, how it blurs things out super well. And so we can actually take this raw image and turn it into this sharpened version with pretty good confidence. So that's what we were seeing as we were approaching. It kind of looks like a flattened disk structure, maybe slightly bowed. Hard to know for sure what we're going to see. Okay, the ground stations were hard at it, as I mentioned. Here we have, at this point, we were 6.6 billion kilometers from the spacecraft. And here we have the Madrid station, antenna number 63 is observing New Horizons. The antenna number 55 was observing New Horizons. Goldstone had all of its antennas observing New Horizons. And the Australian folks had their antennas all observing New Horizons as well. It was a very hard press on the old to observe this. Oh yeah, sorry, the tops are, so everybody at Canberra was observing New Horizons, where only one of the Goldstones, because the encounter happened at exactly the same time as OSIRIS-REx did its orbit insertion. So NASA was like trying to do these two very complicated things simultaneously. And there it is. That is our very first observation as it arrived in the control room of Arrokoth and what it actually looks like. So we were, waiting for the data. We were just sitting there waiting for the data to trickle down from the ground station. And eventually it showed up. And we all have our own computers, but we thought, well, why don't we all gather around one person, have one person bring up the image so that we can all experience this moment together. So that's me in the foreground there. I'm not sure who took the photo. And then we have back here, Alan Stern is the principal investigator for the mission, and sort of cadre of other scientists hard at work here. I purposely wore my Canada shirt that day because everyone else had their US flags on their jerseys. And I just wanted to make sure that we understood that there was a Canadian activity going on here. Okay, so the first thing we saw was this image. This is the Snowman. That is Arrokoth. It's not the best image we have, but this was the one that we started really thinking about what we saw. We can see these two bright dots here that seem to be maybe the basins of craters. And when we see it in really high resolution with the really good images that we got, this is what Arrokoth looks like. So this is what it was all about, was getting to this point. And there's all kinds of details here that we should look at. We've seen this kind of ring here of light material. It appears to be that this is the size of units that make up Arrokoth. So here's like a giant unit of geological material. Maybe there's another giant unit here, another one here. They start to look like clumps of material maybe that has come together. Those clumps of material have a scale that's a few kilometers in size, which is really interesting from a planetary science point of view, because it is kind of the size of primary clumps that we'd expect to form out of a dust cloud. The other thing that we immediately see is there are no craters of any, well, there are craters, but there's only a few of them. So we have a few craters over here that we can see in the shadowed zones. And we can make out a few more along this edge maybe. But generally, it's a very crater-free environment. So that's going to be an important part of Arrokoth's story, is where are all the craters? And what happened to the ones that might have formed? And we'll talk about that in just a moment. And then there's this very large surface feature here that might be a crater, or it might be some other geological feature. We don't really know what that is. And there's the highest resolution color image. And this is the color image. Okay, so here's the black and white, and here's the color. Okay. Now, as we're flying across, we're flying through, I said this whole thing takes just a few moments. And so what we saw just at the very end was this. That is what it looked like. Okay, that is the entire observing campaign of Arrokoth captured in those few slides. But what's really beautiful and amazing success is it exactly fills the field of view of the camera. So we stood back at precisely the right distance. We pointed the camera in exactly the right place. And we took the right sequence of photos to actually make this happen. It's a real engineering marvel. Here it is zoomed in a little bit. This is the black and white image. And we start to look at all the features. This is the point right below the sun. So features here are hardest to make out because they're just brightly illuminated by the sun. So there's not a lot of contrast, but maybe we see some craters here and here. Maybe there's a crater splosh here. It's hard to know for sure. Some here and here, but there's not really, like that's the biggest craters we see. Where are all the craters that should be in between this size and this size? Why aren't there any craters there? What is Arrokoth telling us about planetesimal formation through the truth plate of its surface that tells us what size? Because craters are created by material impacting the surface. So where are the small objects that would impact into Arrokoth? Why aren't there any? And that is one of the real mysteries of planetesimal formation that Arrokoth's telling us about, is that there just aren't that many really small planetesimals. Oh, and that feature there is about 7 kilometers inside. And these small depressions are about 1 kilometer in size. So what happens? Where's the stuff in between? We don't even know if these are craters or these are pits. We don't know. These bright spots, who knows? I'm gonna kind of just go over, I'm not gonna get into this too much, but basically we had all these models that we tried to predict how many craters would we see, and they're not right. It's essentially what it comes down to. You know, if there was a normal crater distribution, we would be way up here. We would have seen something on the order of 1 or so craters per kilometer squared on the surface of Arrokoth, and we see numbers way down lower than that. So there we have a count. That's the official team count of all the craters on the surface of Arrokoth. There's on the order of 45 of those things, instead of the hundreds of things that you might expect. And I'll just skip to here where we see the color. So this is actually what Arrokoth looks like in color. You can see here the bluest material has a 25% slope in its color. So a flat thing would be white. In this plot, no, a flat thing is not white. A flat thing would be super blue. So something that was basically neutral in color, just like white, would show up as 0%. It's not even on the scale. Something that is blue would show up as a negative slope, and something that was red would show up as a positive slope. And the more positive the slope, the redder your surface is. So we can see that the entire surface is red, and some of it is a bit redder than other parts. The stuff near the neck seems to be a little bit bluer than the stuff on the outer sides of the lobes, but the crater bottoms, or the Maryland feature, is mostly red. So we're not really sure what this is telling us about the object, other than that it has a very, very small range of color on its surface. Here's a plot of what the range of slope is. So from the shallowest to the steepest, this is every little pixel on Arrokoth put into a histogram. And so we see that on average, the slope is something around 32%. So sort of like that. And then every other object we know about in the solar system is plotted as another line. And so we see that Arrokoth is redder than Oort cloud objects. It's one of the redder cold classical Kuiper belt objects. It's redder than the outer classical belt objects. It's redder than comets. It's redder than Trojans of Neptune. It's redder than a lot of stuff. It's very, very red, the ultra red material that makes up Arrokoth. Unfortunately, the spectrum that we managed to get is really difficult to interpret. It's so dark, and we flew past so fast. Here's what it looks like with all the spectral pixels that we have looking at Arrokoth. So the black points with the error bars are the spectrum of Arrokoth, and then the red ones are the surface of Pluto that I pointed out. That's kind of that red surface of Pluto. And you can see there's not a bad match for them. There's some places where Arrokoth surface diverges a little bit here and here. But in general, that red material is a pretty good match to what's going on at Arrokoth surface. Where the other spectrum that's showing is Nix, one of the moons of Pluto, as completely not consistent with seeing Arrokoth at all. Although there is this little dip here, and that is an ammonia ice feature. So maybe we're detecting ammonia ice on the surface of Arrokoth. Okay, here are the approach images as we come in. And now you start to see a structure maybe. As we see this spinning object, you can see that although it looks like a nice round thing at the very end, at the start, it's a much more squished and flat looking thing. So what is the real shape of Arrokoth like? So I'm going to show you these two, this derotated view, which is basically if we take out the rotation of the object and just say, what is the perspective that we're seeing? So we're seeing that really, can you see how flat it is just as it turns there? Right? It's not a spherical round thing. Now, we didn't notice this until after the encounter was done. Not anything we could have done about it otherwise, but we start to see that it's in the, if we just look at the approach images, it kind of looks like two round things stuck on top of each other. But if we stop it from spinning around and we just look at the parts that aren't spinning with that 16-hour rotation, we can make out that we're seeing different aspects and maybe it's slightly flattened. And here it is again to try to really figure out what is the shape of this object. Okay, so that is Arrokoth, and there's two images blinking from the second best image and the best image together. And you can start to see maybe a little bit of, if your eyes can capture it, you might see some three-dimensionality to this. You have to stare at it for a few minutes to try to start to see that it really is a flat thing. I'll just play that again so you can see the flatness. So Arrokoth is quite flat. Okay, and then finally we have this. This is the last image that we took of Arrokoth as we flew past it. And here's what we saw. Okay, it's not a lot of data. I'm just going to loop it. But you can see that it's actually a flattened structure. It's not round when you see it from the side. So although it's round when you see it from the front, when you see it from the side, it's actually quite flattened. Unfortunately, that's all we have. That's the last images that we have of Arrokoth, and everything else we do, we have to kind of infer. But this is the model that we then inferred. When we look at Arrokoth, all the data that we have, this is what we think is the most reasonable representation of what that object looks like. It's two round things when viewed face on like this, but from the edge, they're actually very flattened out pancake type things. What we think has happened is that Arrokoth is made mostly of methane ice, and the sun's been illuminating it for billions of years, and that has been evaporating away this ice, that's very CO ice. And as the CO ice evaporates, the side that faces the sun basically is shrinking. So if you started off with a ball and you illuminate this side, it slowly would shrink down. And because of how Arrokoth's spinning and because of its orbit, the edges along here, they're not getting much in the way of illumination, okay? But this side here and the underside are getting a lot of illumination. And we think what we're really seeing is a thing that started off round and slowly contracted down. And that might explain the lack of craters. If we started off with a heavily cratered surface and then we evaporated all the material, that could actually explain why, as you evaporate that material, you lose the crater structure. And also, you would see that there should be more craters along the edge, which is kind of where we see them. It could be an illumination effect, or it could actually be caused by this evaporation contraction. Okay. So New Horizons was like this time machine that went backwards in time to the beginning of our solar system. We think these cold classical belt objects that we've been observing, we think they really are the building blocks of planets that are preserved in the outer solar system. And we're seeing how those building blocks of planets come together and what they're telling us about how planetesimals form. I'll show you one last slide here. Two more slides, in fact. So people ask, where is the mission today? So this is where we are about now. We're currently proposing to NASA to extend the mission. We're way past where we encountered Arrokoth. We're out beyond 50 astronomical units from the sun now. We're one of the most distant spacecrafts currently sending information back. And in fact, it's the most distant spacecraft that we can point and observe something with. It's out there with the Voyager and Pioneer kind of situation. And we think we're going to start learning about the outer edge of the solar system by continuing to do observations. I'll just leave you with this last slide, which is kind of an artist's impression of what maybe was happening with planetesimal formation. Maybe about 4.5 billion years ago, we had these little planetesimal rocks that formed. Somehow they coagulate together. Eventually, two of them get closer. Other smaller ones are ejected, and their removal contracts the angular momentum. It's like the figure skater getting smaller as some of the angular momentum is carried off. And those two things came together and stuck to finally make what we see as Arrokoth today. And that is the end of the presentation. Thanks.
Excellent. Thank you very much, JJ. We have, I don't know whether you noticed, we do have one question. But before we get to that question, I had one question about the star subtraction. Do you use the data that you gathered on that general star field in the later iterations of removing stars?
Yeah, so we basically use every scrap of information we can get. And so, in fact, we're taking data that was taken over the course of a decade to properly model where all the stars are. The best, really what you would need is, it's essentially lucky imaging with a large telescope. You're looking for the best images you took over the last decade. Now, the stars do move, so you can't go too far because they do move, and over the course of a decade, they move far enough that you start to notice it. But yeah, you can use those templates from that far back.
Swapna,
did you want to run through?
Yeah, sure, absolutely. Yeah, thank you very much. Please post your questions in the chat. So we'll start with the first one here. Earlier you mentioned, so this comes from Rick. Earlier you mentioned that you found more objects than expected based on your magnitude limit. Does this mean that there are more objects out there than we thought?
Right. So yeah, so there's slightly more. Instead of finding one, which was our prediction, we found 3. In statistics, 1 and 3 are pretty similar numbers. So we won't, we won't sell the farm or whatever based on that information. But it is an intriguing thing. And so there's actually a program going on with James Webb right now. It hasn't quite started yet, but it's been allocated time and it will begin observing in June, I believe, where they're going to do the same experiment we did to discover Arrokoth. They're going to do that same experiment with James Webb, only over a larger area. And so instead of finding 3 things, they should find something on the order of 50. And that will tell us a good statistical sample of whether there's really more material or not there than we expect. We've been struggling with this question of how many small objects there are in the Kuiper belt, how many 30-ish kilometer sized objects there are for quite a long time. In 2004, we used Hubble to try to measure this. We detected 3 objects in that search. So you get 3 where you might have expected 1. It's maybe not too suspicious. Then we did it for the Arrokoth search. We did the search in a slightly different way. And we found 3 where maybe we should have expected 1. And so now with Webb, they're going to redo the whole thing, only they're going to do it 10 times better and answer this question of whether there's more material or not.
Right. Well, thank you for that. Maybe I have one of those a question too. Why was Arrokoth chosen as a target?
When we found the 3 things, one of them required 190 meters per second to fuel reach. And we knew we could safely plan a mission with 150. So the 190 meters per second was just outside the range where the engineering team felt comfortable. And so it was rejected as a target. The other one was closer. It would only have taken about 90 meters per second to fuel the reach, but it was smaller. And we were worried that it was so small that we just wouldn't get the cratering information we're looking for. The geology wouldn't really be that explanatory. And so we chose this one as the larger object with the modest requirement of 130 meters per second to fuel. Interestingly, because the effort we did for astrometry was so involved at the start, and we did such a good job of locating this thing in space, we used less fuel getting to Arrokoth than was anticipated. So much so that that's why we're continuing in extended mission phase 2. We still have on the order of 100 meters per second of delta V available. Unfortunately, we've already flown through the Kuiper belt, and so there's nowhere for us to really change our course to go to. So we've been searching for about 3 years now, and we haven't found anything that we can get to with that delta V. But we're going to continue searching because we have a spacecraft. It's functioning perfectly well. It has still got fuel in the tank, and we'd like to make sure we make the best of it.
Awesome. We look forward to more stories coming out of this program.
Yeah,
sure.
Exactly. Yeah.
And the last, what's the story behind how the name Ultima Thule came? Am I saying that correctly? Thule came to be.
So the object, as we were approaching it, we were just calling it 2014 MU69 or MU69. And as you're getting closer and closer, the team was like, we do not want to go to the public and say, we've just observed 2014 MU69. This will not capture anybody's memory. You will just forget. We need a name. And there's a story in, Space 1999, where they fly past Pluto and they find Ultima Thule, which is a colony on an icy, rocky world where people have found this paradise on this icy world. And that just seemed to be an okay name to go with for the time being. So there were two, we knew there were going to be two components. So we said, okay, we'll give it two names, Ultima Thule. If they turn out to resolve, each component has its own name. Otherwise, it's one body. This is what we'll use. And we agree at the start, this is not the name we're going to use for the future. We're just using it for this press information today. So then we had to pick a new name. We had a real, an actual long-term name. And we really wanted to connect with indigenous cultures that were relevant to the teams that did this mission. And so the name Arrokoth comes from the languages spoken in the Maryland area. And Maryland is the home of APL, the Applied Physics Labs, that ran the mission. And so that's where the name Arrokoth, that's why that name was chosen eventually. So was to honor that language and honor the mission planners.
Wow, that's amazing. Thank you for sharing that story. Brandon asks, where were you able to accomplish the original goals you had set out to achieve?
So one of the goals was to understand the surfaces of these objects and what the red material is. And that we did not manage to do. We see that it's very red, and we're amazed by the uniformity of it, but the spectrum is just not good enough for us to really know what that material is. And the cratering, though, is telling us a lot about the initial formation of the planetesimals out there. And in fact, we couldn't really have hoped for better in terms of having this contact binary type thing having merged, because there's so many constraints that places on what would possibly be the process by which such objects could form. So that's absolutely fantastic that we had this binary, this contact binary type object. It did all of this amazing stuff to enhance our knowledge of the planetesimal distribution. We're starting to learn more about how these bodies evolve because of this evaporative process that seems to have been going on. So it ticked a lot of the boxes, but unfortunately, we still don't know what this red material is.
Yeah, and on Pluto, it looks so pretty, though.
Yes, that does. And it's scattered throughout the whole solar system. And, it's given the name Folens as kind of stuff that we don't quite know what it is.
So we'll go on to the next question. Yassine asks, how was it calculated that the total mass in the Kuiper belt is only 5% the mass of Earth? Okay, so we basically just counted how many objects there were. So that model I showed you at the start that allowed us to plan the mission, that's a model that tells us every object in the Kuiper belt, it makes a prediction of how many objects there are in the Kuiper belt. And then we just count up all those objects and we measure what their radius is. And then we have to guess what their density is. And the density of Arrokoth, because it's stuck together, and because we sort of know what the strength of this kind of icy material at these temperatures would be, we know Arrokoth can't be denser than about 400 grams per centimeter cubed. And then there are some other objects that we can see that are in binaries, where one's orbiting around the other, and we can get an idea of their mass. And then some of those were fortunate enough that they had occultations, and so we can get a measure of their size, and we get the density of those. And those have densities of the hundreds of grams, 700 grams, 800 grams per centimeter cubed. So we said, okay, let's set the maximum mass by determining how much mass there would be if they were 1 gram per centimeter cubed, instead of a kilogram per meter cubed, and then multiply that by, which is just water ice, right? And then how many objects we have and how big they are. And so that's just a straightforward rudimentary calculation of the mass. That is so cool. Alistair asks, it seems much less red. So the object seems much less red than your Pluto image. Is the Pluto image enhanced color relative to Arrokoth?
Yeah, so in fact, I'm going to share an image from Wikipedia because I get asked this. So here is the image from Wikipedia, which is from the science team. And that is our best guess at making the colors real. Okay, so it's a composite image of all the data that we have. And then we take the spectra and we try to make the spectra, the color of the object, look like we see in the spectrum. But the individual images that we have are black and white images. So each time I show you an actual image of Arrokoth, I'm showing you a black and white image. What's happened here is we've overlaid on top of it a color palette that is reflective of the actual spectrum of the object as best as can be done. So, which is pretty red. It's certainly not though as red as that surface structure on Pluto, where the same basic process has gone into making that color image. So, yeah. So I wouldn't call them false color images because they're not false, but they are manufactured, if that's fair. So,
pretty for sure. Lakshan says, how can you decide for the asteroid's history, like how it was formed, why different characteristics reside on it?
Yeah, and that's, it's a lot of guesswork. Out in the Kuiper belt, in this area where this object is formed, you saw that it's these two lobes stuck together. So we can get an idea of how much gravitational strength is binding those two things together. And that tells us how much it would take to disrupt the pair. And when we do that calculation, we discover that if they're hit by anything bigger than a few kilometers in size, they break apart. So it immediately tells us that the chances that this thing's going to get hit by something a kilometer in size are essentially zero because it's still here. We also see a whole bunch of other binary objects that are orbiting around each other in very loose gravitational binding. And same kind of argument, we say, oh, those things are so loosely bound, if something massive flew past them, they would break apart. And they haven't. So there can't be any really massive material out there. And there can't be lots of small objects that would break these things apart. And because of how we see all these binaries and things like Arrokoth, if the density of material is really low, if there's not very many objects per kilometer cubed in space, it's really hard to form two things, like to get a binary to form. So we believe those binaries form as a primordial thing. We think it's part of the formation process, not that it happens post-formation. Like the Earth-Moon system is a post-formation capture, we believe. But these little things, we think they form close to each other. And another hint of that is when you look at Arrokoth, you see the color is uniform across both things. Why would it be so uniform if they didn't form in the same kind of bulk material? And all of the objects we see as binaries, they are all very uniform in color. So now we have this idea that things form as these binary pairs. They can't be a lot of small material left over afterwards because otherwise they would be disrupted. And they form and they're stable over the age of the solar system. And you put all that together and you come up with various, and then you say, okay, let me try this model of planetesimal formation and see if that works. Let me try this model. And it's hard to find models that work. One of the ones that does work is this idea that a cloud of gas forms in a instability, gas and dust, where material streams into the instability because it's a slightly higher gravitational bump. And that allows material to aggregate and planetesimals form into these bodies, this thing called the streaming instability. It kind of works. There are other similar instabilities that also do the same job. But they're the only way that it works. And so we believe that we're understanding planetesimal formation. We believe that what we're seeing is that, okay, these planetesimals don't form by just dust running into each other. It's the gas building up and becoming slightly overdense somehow, trapping the dust getting dragged into the gas, this trapping mechanism, gravity of that global area gets larger, and now more and more material accumulates onto it, and voila, out come planetesimals. So what you do, and answer your question, is you come up with a story that you think explains the observations. In this case, we actually had the story almost completely laid out before we got to Arrokoth. That whole streaming instability model of planetesimal formation, it was already very well described prior to the encounter, and it predicted most things should form as binaries. And then when you fly past something and you see it is a binary, you think, okay, I think maybe that model is correct.
Very cool for sure. Alistair says, did you say it's evaporating CH4 or CO?
Sorry, yeah. It has both a methane and carbon dioxide ice component at its formation. The methane ice would not last very long and would evaporate away very quickly. And so some ratio of CO and CH4 ice is evaporating out of the surface primordially. And now today, we believe basically all that's left is the CO ice that may still be evaporating slowly. The modeling is really, really coarse right now. And in fact, the people who do the modeling started off saying that it's completely a methane ice object and how would it evaporate away? And then we pointed out to them that it's not a methane ice object. We know that. We flew past it. We measured its spectrum. It doesn't have a lot of methane ice on it. It has a bit of CO ice. So, okay, now they're doing mixture models where they mix in some CO and some methane ice together, and you can still get this evaporation effect to occur. So, and there's a recent paper that we just got accepted, which basically says we think the entire outer solar system is devoid of methane ice. So
Interesting.
it's just it doesn't seem to be that there's any way to have kept it. So yeah.
Oh, very interesting. So Keith asks, have we seen a Kuiper belt-like structure in the extrasolar systems? Any uniqueness or all the same?
So we see all kinds of structures in infrared emission coming from extrasolar planetary systems. And in those exoplanet systems where we see this infrared emission, this extended emission, sometimes we see rings, sometimes we see disks, sometimes we see clumps, sometimes we see spiral arms. There's all kinds of different structures that are being seen. I can probably bring it up really quickly here. Go here. Yeah, there we go. So I can just share this image from AAS website because it's kind of shows some of this diversity. Here we are. So we just see this amazing, these are all ring structures that are around these. So this purple stuff is the dust emitting in the infrared. And so you see some spiral arm structures, or maybe this is a ring in projection. You see these very thin rings. We think this dust is being produced by collisions between small objects like Kuiper belt objects. They collide, they disrupt, dust is produced, and we see the distribution of the material that's causing the dust in this infrared emission. So we do see evidence of these kinds of Kuiper belt structures in all kinds of disks, all over the place when we look in the infrared, but only when we look at really young stars. Once the stars get to be about 100 million years of age, the impact rates are very low between these planetesimals. Everything's kind of quieted down and you stop seeing the dust production. And so the infrared emission goes away.
It's last two questions here. So I'll ask the first of the last two. You commented on the unusual crater distribution. Is it possible that the small objects with high delta V are actually cometary and not conventional Kuiper belt objects like Arrokoth? And this is referring to the impacting bodies.
Okay, yeah, so the thing that we see that's unusual in the crater size distribution is just the lack of small bodies. And this is an interesting thing to connect to comets, because when you see comets, they are small, right? They're kilometer size, 3 kilometer size things. So where are all those things? They obviously show up as comets, but we don't see a lot of them in the Kuiper belt. So it's likely that what we see in the Kuiper belt is a different distribution of material than we see in the comets as they come in, and that there wouldn't probably be very many, like if a whole bunch of comets came through the Kuiper belt, some of them would hit Kuiper belt objects, but in general, that's not going to give you a lot of collisions. And I have actually a little backup slide that I want to share because it shows a bunch of comets and what they look like. And so here is a bunch of comets, and you see that they're 5 to 10 kilometers in size. So Arrokoth over here is 30 by 17 kilometers. These things are half to a quarter the size of it. But what's interesting is that they're not that different in terms of, particularly 67P right? It's got a big piece and a small piece. If you think of Arrokoth, maybe what's happening is that it's evaporating away, tremendous amounts of materials evaporating away. And by the time we see it as a comet, it's actually shrunk in size and it's like this. So maybe they do come from the Kuiper belt and it's just an evolutionary process, or maybe they don't come from material in the Kuiper belt and it's actually a different origin for these things. And that we need to understand that. Sorry, and there was another question as well, or?
Yeah, there's just one last one. So at the beginning of when we introduced you, and your introduction talks about you yourself have discovered some satellites and some objects in the solar system. Would you be able to expand on that?
Sure. So my PhD thesis was on measuring the Hubble constant and trying to figure out how big the universe was. And it's a problem that basically a lot of people are working on. And it involved looking at things that don't change. So we look at distant galaxies and clusters of stars. And at the time, we weren't doing much supernova stuff. So it was kind of like, I found it a little bit dull because nothing was really changing. And one day I was, and this is absolutely what happened, I was just observing away at some dull galaxy and a Kuiper belt object went through the field of view. And I thought, that's a heck of a lot more interesting, actually. And so I started looking for Kuiper belt objects. And one day I was going to go to the Palomar telescope, the 200-inch, to do some observations of Kuiper belt objects. But the objects I wanted to observe weren't available until the end of the night. At the start of the night, it was basically, there was nothing that in my particular program that we could do. So instead, we decided to look at Uranus and see if we could find anything around Uranus, because we've got nothing else to do anyway. So why not point the telescope at Uranus? So we did. We pointed it around Uranus, and we found a bunch of things that were moving, not relative to Uranus. They were moving around Uranus. And it was very sort of shocking, in fact. We didn't, so, it's kind of like a standard science thing. We took this data and we said, okay, well, that was something to do. We'll look at that later. We'll go back to our main program and observe this Kuiper belt object. So that's what's exciting. We flew back to Ontario. A colleague of mine, Brett Gladman, who's at UBC now, and I were analyzing the data. And we thought, oh, okay, we should look through that Uranus data now. And we're looking through it and basically on the phone saying to each other, that can't be. Is there actually something? Was there really something in this data? And we were really very skeptical that we'd found something, but we couldn't convince ourselves it wasn't real. Like it just was there. So we called the telescope and asked them if they could make some additional observations for us in the next coming days, just to confirm that what we'd seen was real. And in fact, it was. And so we had discovered in that serendipitous way new satellites or moons of Uranus. And they were the first satellites discovered from the ground in decades and decades of observing. So it ignited a new little industry of people looking around the giant planets trying to find new moons. And it turns out there are hundreds of little tiny moons going around the giant planets. And so we learned a lot now about the environment of the giant planets by understanding how many of these tiny moons there are. So anyway, so that's all the moons of the giant planets. Kuiper belt objects, we just find them all the time when we observe with these big telescopes and the large cameras. We can find these KBOs, and we're planning to find even more so we can really understand how planetesimals form.
Thank you, Alan. That ends the question and answer round.
Okay. Did I get the job?
I just wanted to thank you, Dr. Kavelaars, for spending time with us today. Really appreciated you spending the time. So thank you so much.
Thank you all for being here. It's fantastic to have such a large audience of people who are interested to listen to this stuff. That's great.
Thank you very much, JJ. That was awesome.
Great. We'll see you all in some other time.
Have fun in Ontario.
Yes, thanks. Bye-bye.
Bye-bye.
Thank you so much.
Bye-bye.